Hey everyone, it's Mr. S, and today we'll be talking about topic 3.8, which is human population dynamics. So as you know, ecosystems have limited resources, and so all populations must hit a carrying capacity at some point. And this was the basis for a theory put forth by the English economist Thomas Malthus in 1798. As you can see in this graph, Malthus noticed that the human population was growing exponentially or at its biotic potential. Meanwhile, our food resources were only increasing in a linear fashion. So he predicted that controls like famine and resulting wars would lead to events that became known as the Malthusian catastrophes. And he predicted that these would limit human population growth or impose a carrying capacity for humans that we'll talk about throughout this video. And these are the factors that and what we'll talk about throughout the video is actually the factors that he did not account for. So why this didn't actually happen the way that he had predicted. All right, so here are the objectives, essential knowledge, and skills. And so the objective for this video is to explain how human populations experience growth and decline. And go ahead and pause the video and read over the essential knowledge you'll be learning if you'd like. The skills that we'll be practicing are describing environmental problems. Okay, so does the Earth have a carrying capacity? So Malthusian theory, which is what Malthus theorized, what I was just saying, was that Earth has a human carrying capacity, probably based on food production, or a maximum number of people that the Earth can hold, right? Human population growth is happening faster than growth of food production, and humans will reach a carrying capacity limited by food. Now, what he didn't take into account was technological advancements. So humans can alter Earth's carrying capacity with technological innovation, right? And so the major example of this is that we figured out synthetic fixation of nitrogen in 1918, which is what synthetic fertilizer was made of. And that dramatically increased the food supply. So basically we're able to find a way to capture nitrogen from the atmosphere and bring it into the earth and use it as a fertilizer. And we take that for granted now, but it was a revolutionary change that allowed for us our food supply to dramatically increase, as you see here, okay? So as we can see here, that while the growth of the food supply in the United Kingdom was relatively linear for about 600 years, there's a dramatic and exponential increase in the 20th century following the invention of synthetic fertilizers. So this is what accounts for the dramatic increase in food production that Malthus failed to account for. However, the most prominent social biologist of today, E.O. Wilson, has concluded that the Earth will still experience a carrying capacity based on the limits of our farmland, and he and many other leading social biologists have predicted this number will be around 10 billion people, will be the maximum that the Earth can carry. We're at 7 now. So this kind of begs the question, will we find a way to dramatically increase Earth's food supply again? And we don't really know the answer, but this illustrates a really important apes concept, which is that predicting Earth's carrying capacity for humans is difficult because future technology can alter resource availability in a way that just isn't possible for other species, and it's hard to predict. Okay, so because most countries on Earth are experiencing population growth, and population size has a really significant impact on the environment, it's really important AP skill to be able to calculate the growth for human population. And we do this by using two human population measures called crude birth rate and crude death rate. And these are simply the number of births and deaths in a population per 1,000 people. So we can calculate the growth rate by subtracting the death rate from the birth rate and then dividing that number by 10, since crude birth rate and crude death rate are both out of 1,000. But growth is always expressed as a percent, which literally means per 100. In this example, we have a global CBR of 20 and a global CDR of 8. So if we subtract 8 from 20, we get 12. And when we divide 12 by 10, we get 1.2, which means Earth's global population grows by 1.2% each year. And remember, we always express this growth rate as a percentage. So again, remember, you just subtract the total number of births from the total number of deaths and divide by 10. You do that because they're 1,000 per 1,000 people, and the growth rate is a percentage or per 100. And then remember that the growth rate is always expressed as a percent. So now we have a really simple formula to estimate the time it will take for a population size to double, and we call this the rule of 70. So all you need to do to determine the time it will take population to double is divide 70 by the growth rate of the population. So using this example of a 1.2% global growth rate, we would estimate that the Earth's population will double in 58.3 years. So all we needed to do there was divide 70 by 1.2. Okay? So once you have the percentage of growth rate, all that's needed is to divide that by 70. And that's going to show you how long it will take for us to double our population. Okay, so here's a practice problem that involves both the growth rate and doubling time. So see if you can calculate the growth rate for a country with a CDR of 9 and a CBR of 18. Then use that population growth rate to figure out how long it would take this population to double. So you can pause the video now and work this out, and when you unpause, the answer will be on the screen. Alright, so here's the solution and the math here. We would take the crude birth rate and subtract from the crude death rate and divide by 10, which gave us our growth rate. And then we would take that growth rate and take it divided by 70. So we would figure out that it would take 77.77 years to double. Okay, so something that we need to think about regarding other factors are the fact that this is a total fertility rate. And so the total fertility rate is how many babies are born versus how much infant mortality you have. Okay, then you subtract those two. And so actually, if there's a higher infant mortality rate, then it drives this number up because people have more children when more babies are dying. So you can make sure you take a note of that, right? That's an important part of population growth, okay? So if the infants are dying more often due to disease, people have more children. And a high immigration level is another big factor, as well as increased access to clean water and health care. That decreases the death rate, and decreasing the death rate actually lowers the population growth. Okay, so a high death rate and a high infant mortality rate will actually increase the population because people will compensate for that. But increased development, education, affluence, increased education for women. When women are more educated, they have kids later and they have less kids, right? And also a delayed age of the first child, postponement of marriage age. All of these decrease the population size. Okay. Okay, and so quickly, standard of living indicators, what the quality of life looks like of a country is based. This is an overall measure of the quality of life that the people of a population experience, and it's based on things like wealth, access to necessities like clean water, stable food supply, shelter, and then even comforts like heat, electricity, and access to entertainment. So the first major indicator of standard of living is an economic indicator called the gross domestic product, or GDP. This is the value of all the goods and services produced in a country. We'll often see it expressed on a per capita or per person basis, which just means we're dividing the total value that the economy produces by the number of people in the population. Then we also have life expectancy, which is a key indicator of the physical health of a population and just the average age of a person in a population will live. Now it increases with access to clean water, healthcare, and reliable food sources. And it's really important to know that as a general rule, the higher the per capita GDP, or how much is produced per person, is affecting the higher life expectancy in a population. So the more developed the nation is, and therefore the lower its population growth as a general rule. So generally, if the country is wealthier, then they will have less population growth. Okay, so FRQ practice is to describe one human activity related to a rapidly growing human population that is having an impact on biodiversity. Propose a solution a government could take to slow population growth. All right, thanks. Good luck.